Okay, this video is on comparing linear functions, and the first thing that we want to note is that the slope-intercept form of the equation of a line, y equals mx plus b, this is often the most useful form when comparing linear functions because our parameters, that is our slope and our vertical intercept, are immediately visible in the form of the equation, and that just makes it much easier to compare different types of linear functions. So let's take a look at what this might look like. In example number 1, it says, with time t given in years, the populations of 3 towns, A, B, and C, are given by the following linear functions. These 3 functions represent the populations of the towns A, B, and C. So now, before I get to the questions here, I want to notice that typically we see the slope-intercept form written like this. The dependent variable equals slope times the independent variable plus the vertical intercept. Notice, however, that these first 2 equations that we have here, they're actually kind of swapped around. Not only do I have, instead of having x and y as my variables, I've got t and p. T is my independent variable and p is my dependent variable. But my terms here are swapped around. In other words, I don't have the slope times the independent variable coming first like I do here, and I don't have the vertical intercept second. Here I've got my vertical intercept and then the slope times the independent variable. So this is still considered the slope-intercept form even though those are swapped around. Okay, so question A says, which town starts out with the most people? Well, looking at each of these 3 equations, I can see that at time t equals 0, which is when we start looking at the populations of these towns, at time t equals 0, population of this town is 20,000, the population of this town is 50,000, and the population of this town is 45,000. So this town, town B, is the town that has the highest initial population. Which town is growing the fastest? Well, let's see. Growing the fastest means it's adding the most people every year. And let's see, this town, it looks like every year this town is adding 1,600 people. This town is only adding 65 people every year. This town is actually losing 300 people every year. So this town, town A, is growing the fastest. Which town is shrinking? Well, this town, since it's losing people, the other 2 towns are gaining people every year, 65 people a year here and 1,600 people a year here. This town is losing 300 people a year, so it's the only town that is shrinking. So town B, not only does it start out with the most people, but it's also shrinking. Now, part D, it says, using a single set of axes, which I have right here, sketch a graph of the population of towns A, B, and C. Okay, so if I'm going to sketch these graphs, I notice that it's going to be easiest, I think, sketching these graphs to start out with the population of each town at time t equals 0. So here's where the time, which I've got on my horizontal axis, here's where time t is equal to 0. And when t is equal to 0, this town has 20,000 people, this town has 50,000, and this town has 45,000. So let's see. Let's put 20,000 down here. So this would be town A. And 45,000 would be, let's say, about right here. And then the town with 50,000 is going to be right here. So now I know where each town starts at time t equals 0. So let's see, for this town, town A, its population is increasing. So I know that it's going to have a positive slope. So its graph is going to look something like that. Let's call this. This is the population of town A right here. This town, the town that starts out with 45,000 people, its population is also increasing, but it's not increasing as fast as town A. It's not adding as many people every year as town A. So this town, its slope is going to be positive. It's going to be going up also, just not as quickly as town A. So here's my graph for the population of town B. Finally, town C, whoops, this was town C, so that's population of town C. Finally, town B, which starts out at 50,000 people, is losing people. It's losing 300 people a year, which tells me that its slope the slope of this line is going to be negative. So this town starts out here, but its slope is going to be negative, so it's going to be going down like that. So this is the population of town B. So there are the graphs. It's a sketch of the graphs of each of my 3 towns. So notice that I can get quite a bit of information out of these 3 equations that are in slope-intercept form. I can tell the initial value of the population of each town, and I can tell whether the population of each town is increasing or decreasing. And in the case of these 2 towns, towns A and C, I know they're both increasing in population, but I can also tell that the population for town A is increasing at a faster rate than the population of town C. So we can say here that in general, the effect of the parameters, we can talk about the effects of the parameters on the graph of a linear function. The vertical intercept, B, tells us the initial value of the function. Sometimes we say the initial value of, we could also say the initial value of the dependent variable. And we saw that in our example number 1. The vertical intercept told us the initial value of the population of each town. If the slope is positive, then the value of the function is increasing. And again, we saw that with the population of the towns. The ones that had a positive slope, their population was increasing. If the slope is negative, the value of the function is decreasing. We had our one town whose population was actually shrinking, town B. That formula for the population for that town, it had a negative value for the slope. And finally, the magnitude of the slope tells us how fast the function is increasing or decreasing. Example number 2. So we're told the cost in dollars of renting a car from 3 different car rental companies and driving K miles is given by the following linear functions. And notice that each one of these linear functions is in slope-intercept form. Here's my slope, and here's my vertical intercept. Here's my slope, here's my vertical intercept. And the independent variable for each of these functions is K, which represents the number of miles driven. And the dependent variable is C, which represents the cost of renting the car. So part B says, describe in words how much it costs to rent a car from each rental company. So company number 1, here's my equation right here. And the cost for renting a car from company number 1, it is 50 plus 0.1 times K. So in other words, it costs $50 plus 0.10. So that's going to be $50 plus 10 cents, or $0.1. 10 cents times each mile driven. So I have a $50, if you want to think of this as kind of the initial cost or kind of a initial fee for renting the car, and then 10 cents per mile. Cost for renting a car from car company number 2, that's going to cost $30, that's my initial fee, plus 20 cents. Let's just say 20 cents per mile driven. And finally, car company number 3. Now notice here I don't have a vertical intercept, or I could say my vertical intercept is 0, which tells me that my initial cost is 0. There's no initial cost or no initial fee. But it does cost me 50 cents per mile driven. Now, next it says graph all 3 equations on your graphing calculator, and we're going to take a look at this tomorrow in class. If you have a graphing calculator and you want to go ahead and graph those. Otherwise, we are going to take a look at these equations tomorrow in class, and we're going to see what we can find out about these equations from looking at their intersection points and determine something about under what conditions it might be cheapest to go with car company number 1, car company number 2, or car company number 3.